Good day to you from Chem Help ASAP. Let's discuss some core aspects of UV-VIS spectroscopy. UV-VIS is truly a foundational tool for analytical chemistry and often is featured prominently in general chemistry courses at the high school and college level. The subject is featured less in organic chemistry classes. As a characterization method, UV-VIS normally takes a backseat to other methods like nuclear magnetic resonance and mass spectrometry and even infrared spectroscopy. Regardless, UV-VIS still does have relevance in organic chemistry, though it is often a tool that is used rather than truly understood. It's a bit like automobiles. There are different ways to interact with automobiles. Maybe you can drive a car, maybe you cannot. Regardless, everyone depends on automobiles. Even if you only walk everywhere, things like your mail and deliveries to your grocery store require vehicles. Perhaps your online deliveries arrive by vehicles. UV-VIS, particularly UV spectroscopy, is much the same way. Organic chemists may not think they rely on UV spectroscopy, but it's often vital in less obvious ways. What is UV-VIS spectroscopy? Unlike IR photons, which interact with molecules by causing bond vibrations, UV-VIS photons cause electronic transitions. So a UV-VIS photon can have the same energy as the gap between two orbitals. An electron in a lower energy orbital gets bumped up to a higher energy vacant orbital. Typically, the excitation is either for an electron from either a filled pi bond orbital or a non-bonding lone pair orbital to a vacant pi star orbital. As light is passed through a sample, the absorption of different photons with specific wavelengths can be detected, processed, and displayed as a UV-VIS spectrum. Here is a representative UV dataset. This is pulled from a NIST, National Institute of Standards and Technology library. These data are for biphenyl, which has this structure. On the x-axis, we have wavelength. As a UV spectrum, we have a UV-appropriate wavelength range of around 220 to 280 nanometers. The range on the x-axis depends on the experiment and can vary. On the y-axis is log epsilon. Epsilon here is the same as from Beer's law, which is absorbance, A, equals epsilon, molar absorptivity, times concentration times path length. I apologize if this gives you flashbacks to general chemistry. Molar absorptivity, epsilon, is a property of a molecule and varies with wavelength. Note that a UV spectrum would record absorbance versus wavelength, lambda. From absorbance versus wavelength, if you know the concentration and path length, one could construct the graph shown, log of epsilon versus wavelength. Those are the basics. We do not need to understand the math to use UV-VIS in organic chemistry, but it's always good to know some of the theory. Okay, that was just a brief presentation on the bare necessities of UV-VIS spectroscopy. Thank you for watching. Like, subscribe, or leave a comment. Take care.